In the previous video, we looked at what makes a nucleus stable and how there are two competing forces in there and how it contributes to the shape of this binding energy graph. Now, we are going to look at, finally, the two processes involved in nuclear processes or nuclear reactions called fusion and fission. Fusion is combining things. Fission is splitting up heavy fat nucleus. And the goal ultimately is to be like iron, steady, and to achieve this region of very stable nuclei. So they will either split up or combine to do that. Let's look at fusion first. So what is nuclear fission? Let's put together a definition for that. So we call a process fusion if two light nuclei, they combine to form a nucleus of greater mass. There we go. The words are finally appearing. The main idea is that they combine. Okay, fuse together means to combine, fuse them together. And they all happen under very specific condition. You cannot simply combine things, you know. So the condition, the first one is extremely high temperature of both nuclei. Okay, you need two ma. You are joining together. So extremely, for example, this one down here, you have deuterium and tritium. You want to combine them together to fuse into helium. You're gonna need both of these to be at high temperature. So high temperature, and make sure that you have enough energy lah, a kinetic energy or whatever. So you have enough kinetic energy to even overcome the potential energy. So enough kinetic energy. But also you must make sure that it is extremely high pressure. And that could be the container where all these nuclei are in. And you want them to be high pressure so that they can collide frequently enough lah. So the chances of them fusing is high enough. So collide frequently enough. If not, they will never hit each other and you're never going to fuse. Okay, so a higher chance of colliding. No lah, collide frequently, okay lah. Collide frequently or higher chance. Let's put that. Higher chance of collision in the first place. Oh no. If you collide but you don't have correct energy, also cannot. So extremely high pressure and high temperature to bring nuclei together. To fuse them together. So let's write that out as the final thing. Ding, ding, ding. Okay, so why do we need so much energy? This one, kinetic energy. Side note, a reminder, you need energy because these nucleus, they repel each other. Okay, remember this one? We look at this in the earlier part. There are forces between nuclei. Nuclei generally are positively charged. So they are not going to just like, oh, I like you, let's stick together. No, you need to overcome the positive repulsion or positive charge repulsion, which is the electric or electrostatic repulsion. Once you manage to get close enough for the nuclear force to take over, the strong nuclear force will pull the nuclei together. But you still need a certain energy. So in the previous video, we look at this graph. Okay, you see a certain force. I can convert this graph, cancel that, into potential energy. Sure, potential energy. So between two, let's say two positively charged particles, one positive here, one pretty far away. If I want to bring this close enough, I have to put in quite a lot of energy to overcome this electric repulsion. Because when it's very far apart, electric force dominates. So I'm going to need a pretty big amount of energy, at least get to this point lah. Okay, and that will be, I guess it's potential energy then. I need to at least put in this much energy. So I put in a big amount of energy to push together these positive charges. Once they are close enough, boom, suddenly something happened. You go down. Pew. So what happened to all the energy that I just put into the system? Gone? That is what we call energy released. So here is work done by me or external force or pressure, whatever it is lah. So work done to push or put nuclei together, two positive charge. I put in a lot of effort to do that. But suddenly, once you pass a certain point in the right conditions, you will be attracted. So in this part, as you're moving down, here you can call it like, work got out, energy come out. So work got out. Yeah, I can't spell. Work got out of system. So I put in energy. And suddenly, a lot of energy come out because suddenly it becomes attractive. Because on top here is repulsive. You're in the positive part of the graph. Suddenly, you are attractive. And that's on the bottom part of the graph. Negative is attractive. Oh, it's written here. Attraction. Okay, so suddenly you're in the positive. So that the thing is work got out lah. Lots of energy come out. The work done that you put in, but even more. Look at this. Oh my goodness, look at this. Look at this level. Very, very negative. Okay, so the process of putting together things release a lot of energy just because of the strong nuclear force. Okay, you put effort to put them together and you release even more energy than what you had in the first place. So let's look at this first example. This is merging together deuterium-tritium to form helium. What is deuterium? Deuterium has a proton and a neutron. So this one is called the H. It's an isotope of hydrogen lah. H 2 1. Tritium is 1 positive and 2 neutron. I just put N lah. So this is also an isotope of hydrogen. This one is 3. That's why it's called tritium. 2 is dew. And this is 3 1. They're all still having a proton number of 1. So they're all still hydrogen. But they're isotopes of hydrogen. Okay, if they are coming in with the correct kinetic energy, correct enough energy to fuse together, and they happen to hit each other, boing, in collision in just the perfect orientation, fusion happens, woohoo! And they join together to become helium. Now this helium is the standard one. Helium, we write here 4 2. 2 because got 2 proton. 4 means there's 4 nucleons. And also there's 1 extra neutron. Why got extra neutron later we see. Okay, so we can write a nuclear reaction equation, a nuclear equation or a chemical equation for the reaction here. So what happened? What did I put together? 2 1 helium plus the one down there, tritium, 3 1 hydrogen. This is the tritium. And then I draw an arrow to represent the process. Some kind of reaction happened. And what comes out? Helium. So right here, helium. 4 2. Now, chemical equation and nuclear reactions equation like this must be balanced. So we do a quick check. Proton, 1 plus 1 equals to 2. Looks okay. 1 plus 1 equals to 2. I'm pretty satisfied. Let's check the nucleon number. 2 plus 3 equals to 4. Huh? Something is funny. No. We need to add something. We are missing a neutron. So neutron, we just say there's 1 nucleon, no proton. So 2 plus 3 equals to 4 plus 1. That seems better. Okay, and don't forget, there's a whole bunch of energy can be released in any form in, I don't know, what radiation you want, you choose lah. But lots of energy coming out. These are what we call the reactants. Who is doing the reaction? Who come together? And all these on the right are the products. And the products can have a certain mass, total mass. Reactants can have a certain initial mass. The missing mass will be who? Energy release law. Okay, so this energy release here will be the change. Let's make a note here. Change in binding energy, which can also be calculated from the mass defect of all your products. Here got a certain mass, here got a certain mass. The missing mass, energy law, all become energy liao, all release. That is how you can think of fusion. Now, a classic example of our experience of fusion every single day, especially if we live in Malaysia or somewhere near the equator, is why is it so bright and so hot? That's because of the sun. Make us sweat and burst. So the sun actually, why is the sun so hot and so bright? That's because the sun is a nuclear fusion reactor. The sun releases huge tons of energy, and that's because of all the nuclear fusion processes happening in the sun. Here's one example of a reaction in the sun. It's not just one step fuse, You see got so many steps. Oh my goodness. So every time you fuse, got all kind of energy coming out. So imagine the madness, the amount of energy the sun is throwing at us. Although we are so far away from the sun, if you're at the surface, die already. So let's write a few more equations to practice thinking about this. There are usually 3 steps to this fusion in the sun. The very first step is just hydrogen coming together to form deuterium. So this one, we can write it as something like this. Both cases are up here, path 1 and path 2 down there is the same identical thing. So we will say that 1H, what is 1H? 1 1. I don't know why they write 1H. A bit funny. A proton plus proton come together. React. You got H. Ooh, some magic happened here. This one, you have 2 nucleons. One of them is a proton. So one is positive, one is neutral. Neutral is the white color one. But you also release some other extra thing. What is that? Well, it turns out that in some reactions, you can also have other products like the anti-neutrino and a positron. So these are old friends from our particle physics in AS. Anti-neutrino, electron, anti-neutrino or electron. This is the positron, a positive version of the electron. All these can also come out as products. That'll be the first one. Step 2, what are possible? How will we write out this equation? So you are fusing together hydrogen and deuterium together, and you get tritium. That's if you want to make tritium in the sun. So you have H21 plus H11. Some process happen. We use the arrow to show something happen. Then you get 3 nucleons. 2 of them are protons. Plus a bunch of gamma energy. Wow, this one is going to be some photon, X-ray, UV light, visible light, whatever you want to do lah. I'm just going to leave this to you. E equals to HF or HC over lambda. So the sun is throwing out positron, anti-neutrino, but also throwing out photon at you. Wow. And also energy. Okay, never mind. Last stage. So the last step of fusing together to get helium is this one. So now we have tritium, 2 tritium. So we have this thing. Oh, helium, sorry. Why did I write that H? This is helium, not tritium anymore. Helium 3,2. Yeah, change element already. So you want helium 4,2 to be more stable a bit. So it's helium 3,2, helium 3,2. React, you get helium 4,2 plus a bunch of other stuff, which in this case would be more hydrogen. There we go. And a bunch of energy. I didn't write energy inside here. So what happens next is this hydrogen can go on to combine with other people lah. You go back to step 1. Combine again. As long as if you have hydrogen, you can keep doing this process and releasing so much energy and so much photon, radiation, everything. And in the sun, actually it happened in layers. Remember, eventually we can fuse and then we become iron. The binding energy graph. Where's my binding energy graph? This one. As long as you're on the lighter side down here, you can keep combining until you reach iron. Then that's the furthest you can go in terms of fusion. In the sun, actually, a lot of elements all get combined and created when conditions are right. So on the outermost layer of the sun, that's when you have your hydrogen fusing together to form the second layer, which is helium. So hydrogen joined together become helium. Helium joined together become carbon, oxygen, neon, so on and so forth. But at the very core, you stop at iron. Because this one is already the most stable nucleus. Highest binding energy. You will not continue to fuse beyond there. But this is also a bit scary, you know why? That means our sun and all the stars have a limited fuel. And the fuel of fusion is hydrogen. Hydrogen become helium. Eventually, if hydrogen run out, then what happened to the sun? If you run out of fuel and your sun start to have a lot of iron, this is the end game. Your sun is going to die. Eventually, we'll have a stellar death lah. So the sun burning bright suddenly become a bunch of iron, die already. So it will either explode, it might implode, it might become a black hole. Go and Google up. But know that the sun has a limited lifespan, our sun, and that depends on the fusion process. How far is our sun down in this chain? We still got quite a few years, scientists estimate, but when the sun goes, so does our solar system. So thank the hydrogen that we still have fuel in the sun, quite a lot of hydrogen. So our sun is fairly young, not too old, but older suns will have more of these heavier elements fusing together. Because you're near the end of the chain, that's the end game now. Alright, so that is fusion. Let's move on to the next one, which is fission. So nuclear fission is a typo in the notes. Nuclear fission can be defined as the splitting. You break down. So this one is an important word. You split apart. Splitting of a heavy nucleus into 2 lighter nuclei of similar mass. a similar mass. Okay, so you break them into two small sections. A classic example would be this picture down here where you have a uranium-235. Wow, so big, eh? Look at the number of proton. If something causes it to be unstable, it can start to split like cells, suddenly boop, boop, become two, and then it become two daughter nuclei of like different elements. And you know, you have different proton, you have different element. Okay, and this happens under a certain condition. So let's write down what initiates this reaction. So fission is initiated by a neutron capture. So you say a capture of one neutron. Oops, I can't spell. Capture of one neutron into the nucleus. Okay, in nucleus of a high neutron to proton ratio. So this part is just an extra information for you to know. So what is high neutron proton ratio? That's referring to the elements down here, the heavier ones down on this chart, or the elements down on this end. See the neutron number so big, eh? Proton number not as big, eh? This part, these are where all the fission can happen pretty actively. The whole idea is that your big fat nucleus is already not exactly stable. I mean, they could split up naturally, but it depends on the probability, and it may not happen when you want it to. So you're going to take a gun, a pew-pew gun, and you're going to shoot some neutrons and bombard it with one neutron. All it takes is one neutron. And see what happens. When I shoot a neutron in, pew, it becomes unstable. And does it split? Oh, it splits into two daughter nucleus. So that will be barium and tritium. We call them daughter nuclei, you know, parent, daughter. So it's kind of like this lah. You imagine you have a friend group, a big group, big group, not very stable, got some tension between some people. Suddenly you throw in one issue. Wow! Everybody is just and then just break apart into two friend groups. I don't know. That may be high school drama or school drama or college drama for you guys. But that's what's happening here when you bombard nucleus with an electron. So for this fission reaction as well, we can write a nuclear equation for that. Let's start off with what is in the beginning before anything happened. So here is you're bombarding a nucleus into uranium-235. So we have uranium-235 nucleons and 92 protons. And we plus this little troublemaker, the neutron that come in and bomb things. Okay, then something happened. Oh no, fission happened. The process happened. What do we have? What are our products? We have a few krypton, barium, energy, and a few neutrons. So we can write that out as 9236 krypton plus 14156 barium. And we can do a quick check of our nucleon numbers. 235, 192, 141, and you do double check what is missing. You realize that we need to include the neutrons as well. So there should be neutrons, but 3 of them. So it's 3 times of this. And of course, a bunch of energy lah, if you want to write that in. Sometimes you don't write that in, that's fine too. So this is our nuclear reaction equation, and where we have a few reactants, and we have a bunch of products. If we ignore the neutrons, I guess we could just look at the uranium, krypton, and barium. Okay, so this one is an example of a very common fission reaction. Now, how do we know if this is energetically possible? Can simply just split meh? Yeah, there's a way to check, but we gotta talk about the energy language. So we know that this energy here is going to be the change in binding energy. A little bit more on that. Hang on a second. So change in binding energy. So why is it possible to have this splitting up? Let's look at this, underneath this graph, there's this past year question, just a snippet of it for us to look at. So we knew we need to compare binding energy. Uranium is starting off where? Right at the end here. Somehow you're going to go towards iron, right? The ultimate goal is to become iron. So we are going to talk about the total binding energy. We'll compare the binding energy of this and compare the binding energy of these two products. So we're going to say the total binding energy for what are those two? For barium and krypton, both added together. So we have a total Be is greater than the binding energy for uranium alone. And that's why it's possible to have this reaction happen. So baryon, krypton, they are somewhere. Where is baryon, krypton? Somewhere along this side. But uranium is here. So of course you can have some kind of reaction that allows you to split up and become more stable, have a higher binding energy. Right? So that's how we can check if it's energetically possible or not. And remember, as you get bigger and bigger, you have a lower binding energy. Lower BE for larger nucleus. And that is not very good because your strong nuclear force, which is what we want, that's great, we like the strong nuclear force, is only felt between neutrons that are close together. And if your nucleus is so big, you only can feel each other, the neighbors. But then your Coulomb repulsion force continues to be felt throughout the entire nucleus. So you are repelling everybody in the nucleus, but strong nuclear force, only your neighbors you attract. So you can see here, you have electrostatic repulsion, which can act across all protons, but nuclear force only between your neighboring kind of nucleons like that, only in a localized position. Whereas repulsion, anywhere you want to repel, you just repel. You don't like who, you just throw only. Okay, that is going to be, I'm going to draw some graphical representation of that. Okay, so the bigger you are, the more unstable, instability, and you have a very fissile nature for heavier elements. So a lot of heavier elements on the periodic table got radioactivity they will break down they're not very stable. For this reason, because they are big. That's all. So one use of this process, this fission process that we see a lot, is in nuclear reactors when we're trying to use this energy created. You see this energy here? Wait, let me highlight for you. Energy. This energy is a lot. And we can better control fission better than fusion. So humans decide that, we can use this process to create energy for us. And in a fusion reactor, a chain reaction usually happens. So chain reaction. What's a chain reaction? One neutron bomb one neutron, or bomb one nucleus. Then you will release 3 neutrons to bomb other people. 1, 2, 3. And then you keep on bombing. Soon everybody will all be having fission. So the idea of a chain reaction is, if you have 1 nuclei, you just bomb, then 3 protons come out. That's it. Very chill. But in actual fact, when you are dealing with a chunk of uranium, if you have many uranium and you bomb one fella only, one fella, you see what happened? I bomb you, you bomb me, you go and bomb 3 other people. It's like, even my computer is lagging. It cannot even deal with this chain reaction happening right here. But you see, in the process, lots of energy is released. So in the early days, people unfortunately had this idea and said, what if we put this uranium in a container, turn it into a bomb, what we call the nuclear or atomic bomb, and throw it on somebody else's country, or even test it on our own people. Now that is unfortunate because then this was the rise of atomic and nuclear bombs. These are weapons that countries race to create because it gives them power and you can use it to threaten other people. But it has been used in the past a few times before, unfortunately, and the results are catastrophic on the people that stay there. So that's the sad part of it. I hope that in my lifetime, I will never have to see this mushroom cloud, and I hope you will not have to see that too. So nuclear warfare is not nice. It leaves a very long impact on the survivors, and it kills the rest, all of them. Not only that, it impacts the environment and leaves radioactive decay and waste, and all kinds of things happen for years after a bomb drops on a location. So humans got a bit better after they tried bombs on people, and they're like, oh my goodness, this is a bit too powerful. You can go search out some of the testimonials of survivors of the atom bomb, the nuclear bombs, and it's very grim okay. And anyway, so people say, okay, maybe bombs not a great thing. Let's do electricity. So they're going to use this chain reaction thing, but in what we call a nuclear reactor. Now this is much more controlled because we are smart. Humans have figured out that, okay, the cause of all this, the cause of all this chain reaction is because of all these neutrons flying around and hitting other uraniums. But if we put a neutron absorber like this one right here, then it will absorb the neutron and then you will protect other uranium from undergoing fission as well. So people decided to say, okay, let's do this. We can insert these absorbers to control the fusion reaction. Okay, maybe I put it here. And then when I fire neutrons, not everything would go off at once. So let's fire neutrons. Okay, so we got some reaction happening in our fusion reactor with the control rod halfway there. You got some energy here, some energy there, fire neutron again, here a bit, there a bit. Pretty controlled. Now if I take out these absorbers a little more, then the chain reaction will be a little bit more active, because then you are free to affect more uranium nuclei in the reactor. So I mean, you can take it up all the way. There unfortunately also have been disasters related to this. See, if I take the control rods all the way out, a much larger power output, but also very dangerous if your nuclear reactor cannot contain this energy or some explosive stuff happening inside there. So I'm going to insert it all the way in, scram the reactor, we call it. Once we stick the rods in, the reactions should calm down and the power should drop back down to 0. So yeah, we can control fusion pretty good, but disasters happen. So in 1986, there's a Chernobyl nuclear disaster. They created this nuclear power plant, but something went wrong and a disaster happened. Classification of severity level 7. There are quite a lot of movies on this, so I encourage you to go check out some of these movies on Netflix or YouTube or whatever and see about that. A more recent one that you may remember if you were alive or born yet is the Fukushima disaster as well. This one can be quite severe. It's the severity level is classified to be level 5 to 7. Also not very good for the people there and also the surrounding and the ocean in that area. So disasters do happen. People try their best to be careful, but at the end of the day, these are nuclear stuff. So you don't want to play with all of these. If you ever go into nuclear physics, please be absolutely sure you know what you're doing and why you're doing it. Because yes, it gives you lots of energy like the sun, like atom bombs, but in a nuclear reactor. But with great power comes great responsibility. And this is literally an immense amount of wattage power. We talk about power the physics way. So to end the video, let's summarize the difference between fusion and fission. So fusion means to combine. So you see this picture, two things combined together, release energy. Okay. Whereas fission, you divide or split up a nuclei. So one nuclei split into two. Okay, this one is combined. And as you split, you become nuclei of smaller nuclei of similar size. So two products, they'll be roughly the same size. Okay, but the ultimate goal is to be more stable. So the binding energy per nuclei will increase in both types. Because you want to become like iron. You want to be stable at top with the highest binding energy. In fusion, you are initiated by very high temperatures, which means high pressure also. Then only you have conditions to overcome repulsion and join together. In fission, who starts this thing? The neutron bomb something, then become unstable and split up. So this one is a neutron that causes and starts the fission process. Last one, both processes pretty much release lots of energy. Lots and lots of energy. But fission releases neutrons. I guess fusion does as well. So plus neutrons in some types of fusion processes. That's how to compare both of these two different nuclear processes. Make sure you know how to tell them apart. And make sure if you ever do some kind of work related to this in the future, that you take it seriously. And remember, at the end of the day, we are just mere humans that will be easily overpowered by any of these kind of nuclear processes. Although they might be a good alternative to energy in the future. So that's all for this video. I'll see you in the next ones where you'll see a couple of examples dealing with fusion and fission, how to calculate, how to explain, how to understand the graph. So that's all for this video. Bye bye.